Alright, we will be discussing about a force that always acts towards the center, or we call it the centripetal force. Centripetal force, or we can use this symbol, or this F sub C. That's centripetal force. It's a center seeking force. It needs to be pointing towards the center. And as we can recall, the unit of force, since it's a kind of force, the unit of force is Newton. And 1 Newton is equivalent to 1 kilogram meter per second squared. Just a review, okay? And another thing to know before we will go further with the topic, what causes acceleration of a certain object? Definitely, our answer will be force, okay? And our topic for this moment is centripetal force, a kind of force, very general or generic, because we have a lot of forces that will act as centripetal force that will point towards the center. And if we have a center-seeking force, it will the object that will experience the centripetal force, it will be moving in a circular manner. It doesn't look like a perfect circle, but the object will move in that direction. If this is the object, it will move like counterclockwise because of centripetal force that is pointing towards the center. Okay, if ever this will be our center here. Okay, what are the forces that will act as centripetal force? We will try to find out later, but we will have one more thing to review. If you could still recall, okay, if we have a ball here and then we apply some force or an applied force to that ball, where does the ball go? Okay, if we have a force that is having that right direction, then the ball will also move following the direction of that force. So it will also move to the right. Okay, does it make sense? A force applied to the ball, going to the right, and the ball moves to the right. Okay, and if I will ask you, if we have an acceleration, because force causes acceleration, and we have a centripetal force, a center-seeking force that maintains a circular motion of a certain object, where does acceleration vector, or the direction of our acceleration in this case? Okay, so if we have a force, this is our centripetal force. It moves towards the center. Of course, it's a center-seeking force. Therefore, our acceleration will also be going along with that direction of the force. That's specifically the name of the acceleration involved in a centripetal force concept is the centripetal acceleration, or we can use this symbol A sub C for centripetal acceleration. It goes along with the centripetal force. Okay, please remember that one, because the object will accelerate following the direction of that force. Okay, and we will be discussing now the type of forces that will act as a centripetal force. So forces acting as centripetal force. Again, centripetal force is a generic term for a force that is pointing towards the center. But we have a lot of forces that that act as a centripetal force. Let's say, for example, we have the tension force, or Ft, and we do have the normal force, Fn, and we have static frictional or static friction force, or in physics that's since it's static, must be S. Okay, and sometimes this is a common force that sometimes help in as additional force for the centripetal force. We have the gravitational force, or Fg. Okay, let's talk about each forces. Again and again, these four forces that I introduced, they will act as the center seeking force. In general, we call it centripetal force, but the specific force that acts as a centripetal force could be one of the following. Okay, tension force, if you could still recall, if it has a rope or string, if the object is attached to a string or rope, okay, that string will have a tension force that will act as a centripetal force. If ever that you tied an object on a string and then you move it, it will again move in a circular pattern. Let's say this is your hand at the center, and then you have this rope here with an object tied to it, and it moves, let's say, in clockwise. So after some time, the object will move at this point, and the reason why it has a circular motion, because the tension force acts as a centripetal force. Okay, so our centripetal force in this case is the Ft, because we have a rope. Okay, a rope, or let's say a string. For a normal force, we can observe normal force acting as a centripetal force in a Ferris wheel scenario, along with gravitational force. They go hand in hand. This gravitational force will help acting as a centripetal force. Okay, in a Ferris wheel. There's no rope involved, but object is placed on a rigid or strong or solid material. And another definition of normal force, it's always perpendicular to surface. Okay, I will try to draw. Okay, let's say, for example, we have a table here, and we have an orange on the table. Okay, there you go. So, as we all know, this is influenced by a downward pulling force of gravity. It pulls down the orange, and since it is placed in a rigid, the table is a solid object or a rigid object, not a rope, not a string. So the force that will balance our object here, it's the normal force. Okay, it balances the gravitational force. That's why the object is there resting. These two forces are balanced. Okay, and yeah, on a Ferris wheel, or in a Ferris wheel, they will also work hand in hand. Okay, as the Ferris wheel will move, Okay, I will try to show that one in some time. Okay, maybe, yeah, I will try to draw it also. Okay, I will try to erase first this representation of normal and gravitational forces. And let's say we are in a Ferris wheel. In a Ferris wheel, there's no rope, but these are very rigid metal. So that rigid metal, they will be, it looks like a stand fan, but it's a Ferris wheel. I will label it here, Ferris wheel. Okay, now there's no rope, so it's not tension force that acts as a centripetal force here, but it's the normal force. Okay, so let's say that the cabin, I don't know if that's the right term, cabin is here. It is being pulled by, when you are riding on a cabin of a Ferris wheel, when you are at the bottom, the gravity pulls you down and balanced by, I will use separate color, another color, red, balanced by the normal force. You could feel it. But if this will rotate and you are already at the top of the Ferris wheel, look what will happen. The gravity helps. The gravity helps in, or the gravity helps, or like acts as a centripetal force. Now it's going towards the center, and we have like a tiny normal force here. That's why when you're above, you feel like your weight is like lesser than you're at the bottom, because the normal force at the bottom will act as a centripetal force, and when you're at the top, the gravity will now be much more of a centripetal force than the normal force. When, let's say, you are in this position, so the gravity be here, okay, and then the normal force is going to the center, as it is the centripetal force. Okay, same is true when you are in this, when you are in this position as the object moves. Okay, so gravity pulls here while the normal force is trying to be the centripetal force. On a Ferris wheel, always remember the normal force is our centripetal force, and then the gravity backs it up. It helps acting as the centripetal force, especially above position, this position. Okay, and I will continue. We have the static friction force, but this time I will use a drawing or a representation. I will try this one. Okay, to discuss about static friction force, or okay, the static friction force is our centripetal force in this scenario. Let's say, for example, we have a car, and then this is the road, and you have the tire. It's the tire of the car here. okay, it will create like a friction, specifically static friction. And this friction created between road and the tire, instead of like, you know, going to this direction without the static friction, the car will eventually go there and there must be accident probably. But with the static friction created between road and the tire, the object will feel like there's an inward force, because we can imagine that this is like still circular because the car is moving around a curvature. The static friction force will be the centripetal force once the object will move along a curvature or like a curved road curvature. Okay, and road and the tire will make this static friction, and static friction will act now as a FC, centripetal force. And again, the blue thing there, it will go along with the direction of the force. That's our centripetal acceleration. And this violet here, the violet thing, it's the velocity, the vector of velocity. Okay, remember, it's meter per second, the unit of velocity. That's how I tried to, you know, help you understand that we have a lot of different forces that act as a centripetal force depending on the situation. Okay, now, so I will be revealing the different variables needed in calculating centripetal force. Okay, again, we have specific forces that will act as centripetal force, a center seeking force. Okay, let's say for example, this is a hand holding a rope and we have a certain object there. Okay, and since it's a rope, so the force involved there is the tension force, right? Because tension force has something to do with rope, then attached by the object, then you move it, and it will act now as our centripetal force, especially if you will move this object in a circular manner. It's not a perfect circle. I will change it. I guess it's better. It's rotating counterclockwise, and then at some point the object will move in this direction or in this position as it moves counterclockwise or in this direction. So we have a center seeking force that will always points towards the center. Our centripetal force is the tension force. Okay, and another thing, since we already have the centripetal force in our situation here, and force causes acceleration. Acceleration, in this case, acceleration is our centripetal acceleration to be specific. So our AC, please remember this one, the magnitude or the value is constant all throughout the rotation or the circular motion, as long as it's uniform circular motion. Okay, and but if you notice, direction is changing, so it's still accelerating. The object is accelerating since we have a change in direction here. Okay, and where are we going to draw our acceleration vector? So force causes acceleration, and the acceleration will follow the direction of the force. Since the centripetal force is towards the center, our acceleration will also be towards the center and constant all throughout the motion. Let's say, for example, it's 1.5 meter per second squared, 1.5 meter per second squared, and yeah, 1.5 meter per second squared. Constant, but the direction is different. Imagine it's pointing towards this direction once the object is in this position. But when it rotates and be in this position, now the orientation of its vector changes. Same with this position. So therefore, acceleration's direction, or the centripetal's acceleration's direction is changing. Okay. What about the other variable, since we are dealing with acceleration? So another variable is called velocity, meter per second, and it's a vector. So where are we going to draw the direction of velocity? Since it's moving counterclockwise, let's say this is going to be our reference, this one, this object here. So the direction of the velocity should always be like perpendicular to our acceleration and force. Since the object wants to move in a straight line, if there's no centripetal force, this object will fly out in that direction. Okay, but since we have centripetal force, so it will maintain its circular motion. Okay, once we have this object here, our centripetal force will be downward, not centripetal force. The velocity is downward. In this case, it will be moving towards this direction. So if you notice, direction is changing. Direction is changing. But please remember, magnitude is the same all throughout the circular motion. Okay, so let's say we have 2 meter per second here, we have 2 meter per second here, and 2 meter per second here. It's just the direction changing, but the magnitude constant. Okay, and not last, but second to the last, we need to know the mass of our object. Okay, mass in kilogram. Okay, we need to know the mass of our object here. Let's say this is like 4 kilos. It will not change once it will rotate. It will remain 4 kilogram. And one more variable to complete our formula later, we need to measure the distance from that object. I will use another color. Okay, I guess brown, I don't know. Okay, so we will try to measure the distance between the object and that center here. That's half of a circle. We call it, this is our radius, okay, in meters. So the needed variables in order to calculate centripetal force, we need to have the constant acceleration, okay, constant, and then we have to know the mass. Of course, it's constant also, it will not change. We need to know the velocity, and it's still the same, constant velocity. And what else? The mass, we already mentioned that one, but yeah, don't forget radius here. Okay, and yeah, one more thing about velocity. This is one variable needed in calculating the centripetal force. Velocity is a vector, meaning it has magnitude and direction. Okay, let's say for example the magnitude, it includes the unit. Okay, let's say 2 meter per second. So this is magnitude. And it has a direction, let's say north or upward or whatever it is. So that makes velocity different from the other variable. If we will remove direction, we only have magnitude of our velocity. If that's the case, our velocity will become this so-called, if it's only magnitude, speed. Okay, so the speed in our uniform circular motion, or abbreviated as UCM, it's constant, because without direction, the magnitude of our velocity is constant, if you could still recall. Okay, so no direction, it will become the speed, and it's constant along the along the uh, rotation. Okay, so in this case, this is the only variable that is constant in a uniform circular motion. The velocity, let's say magnitude, let's try to compare, and then we have direction here since they are vector. Velocity, the magnitude is constant, but different direction. So it's not constant at all because direction is changing. Now we have the centripetal acceleration. Magnitude is constant all throughout the rotation, but yeah, different direction. So it's still not constant along the way because of the different directions once the object rotates. We have mass. We have mass of the object. It's constant, and mass doesn't have direction, so yeah, it's constant. And then we also have the speed. The speed is constant since speed is a scalar, not a vector, so no need for direction, so that's constant. Radius is constant along the rotation in a uniform circular motion. Okay, it's constant. What else? We have velocity, we have acceleration, we have mass, we have speed, and we have the radius. Okay, and we have force. Okay, we have centripetal force. Centripetal force depends on the value of your velocity, acceleration, mass, speed, and radius. It depends upon the situation because centripetal force in a Ferris wheel varies in magnitude because we have the combination of the gravity and the normal force. The net force of these forces will be the centripetal force, so it changes in different position. It depends upon where the cabin of the Ferris wheel is situated along the rotation of the Ferris wheel. Okay, but in tension force, if our centripetal force is tension force, then it's still constant in that case. Okay, so we have mass constant, we have speed constant, radius, and centripetal force. If the force is tensional force, a rope, and then you rotate the object tied in that rope. As long as it's uniform circular motion, so tension force is constant all throughout the rotation. Only the acceleration and velocity is not constant due to their direction. Okay, that's it. Thank you for listening, and I hope you learned something from this video, and I hope you will share and like and subscribe to this channel if you're new, for me to have the motivation to create more videos like this. Thank you so much.